So good afternoon, friends. Hearty welcome to this another webinar that we are organizing at CLE platform. And today, once again, we are privileged to have with us Sharad. Sharad Saxena is a friend and one of the most passionate teachers that I've met. Professionally, he has worked in the corporate sector, as we had written in that flyer. So as you probably know by now, he's worked in various companies like railways and some banks like Bank of Baroda, etc., heading the technology, the IT divisions. That has been his professional experience. But for several years now, he has almost fully devoted himself to developing interesting ways of teaching science based on experiments. These are very simple, low-cost experiments that he has devised, and he himself has been conducting a lot of sessions for children, both in offline and online mode. And he's also been involved in training teachers, teachers of science, and we have here Sharad. And without wasting further time, I'll invite him. He'll talk about how to make science interesting through experiments. And even if some of you are teachers in non-science subjects, I'm sure you will also find it useful. And there'll be some interesting ideas that you can take away from this. So Sharad, all yours now. And we can keep some time, Sharad, at the end for Q&A, for interaction as well.
Thank you, Rahul. Thank you so much. Thank you for the introduction.
Thank you. Thank you. Thank you for your time, Sharad. We are privileged. It's all yours.
Yeah, thank you. Privilege is all mine because I'm so passionate about this particular aspect, as Rahul said, and any opportunity like this is most welcome. Those of you who have attended our session, Bama, Ramesh and myself, we had 12 sessions with Echo, and some of those will be repetitions here, so pardon me for that. I can see some names being there, but largely, as Rahul said, that what I would be covering is how to make science teaching exciting, and why inherently it has to be exciting. I'll cover that part as well. I mean, without we making exciting, it is indeed exciting to us as human beings. That's one. Second is some of the techniques which I have used in the past and appear to have worked. I'll tell you about that as well. And I'll introduce you to a tool many of you might be aware, since you are many of you are teachers, an open source tool which will help us make the students understand the concepts much faster.
Yeah, so that will be very useful, Sharad. And I think many of us may not be aware. So it'll be good to know about that as well. Yeah, definitely.
Yeah. So this is what pandemic has done on the left-hand side. This is how the students mostly look like, unlike on the right-hand side where attentively listening and focusing as well. Does our class something look like this? Why? So do we have such noise in our science classroom? Do the children shout like this, overjoyed with what they see? And this particular piece of experiment is nothing but Newton's color wheel. I was holding a workshop, as you can see, a lot of things lying around. And the first one which we made, a kid had colored the wheel, and we rotated it, and it became white. And you see the excitement. Just hear it all over again. Why? So can we have such excitement in our class? Can science not be boring? Boring is a very, very far-fetched word I have used, but science can be so exciting. And can we have such noise in the class? This is what is our attempt. Sorry. So I am recently reading a book, and I pleasantly came across a wonderful section in that book. The book is Righteous Mind by Jonathan Haidt. He's a moral psychologist, so the subject is very different other than science. But what he writes in that is very striking. He says that infants are born with some knowledge of physics and mechanics, And he has done some experiments to prove that. They expect that objects will move according to Newton's laws of motion. So actually, you don't have to teach them Newton's laws of motion, and will get startled when psychologists show them scenes that could be physically impossible, such as a toy car seemingly passing through a solid object. And all along, even before I read this particular part of the book, I had a firm belief that our mind is wired for physics. And I'll give you some examples, and I'm sure you'll be able to add to that. So as we go along, but I was very happy, and I thought, let me copy this quote for you, that somebody has scientifically proven that our minds are wired for physics. So as Rahul was saying, normally I do experiments with the things which are either available at home or which we can buy off with a very, very low cost, less than 50 rupees. So a very small experiment to show a beautiful concept, a beautiful principle to begin with, and how it is being practically used. I'll just take you through two experiments. One, here I'll explain to you the part of it, and second one, I'll show you something else. So two such experiments, and then we'll get on to something else. So what do we see here is an ink dropper. Not many of us use it anymore because there are very few fountain pen users these days, and fountain pens are all now equipped with pumps and all. They've become very sophisticated, but in our childhood, we used to, if we were not skilled enough to pour it through the bottle, we used to use this dropper. So what I've done, I've just modified this dropper a little bit. I've put a screw at the bottom, as you can see here. Let me take a pen. Yeah. So this is the screw I have taken, and I have put some hot glue over here so that it doesn't slide out. Now the experiment, just see this.
As you can see, the dropper is floating in the water. The weight is attached here, but the water is filled up to here, and this portion up to the top is air. And because of the buoyancy of the air, the dropper is floating. Now, this dropper will obey my commands. I'll say, dropper, come down. And it comes down. I'll say, dropper, go up. It goes up. I say, be there in the center. Stays there. Why is it happening?
So a very small experiment, hardly costs you anything. And what do you think? What principle we would associate with this particular experiment?
Press the bottle, maybe. Did you press the bottle?
I did, Lata. Yeah.
Lata caught you, Sharad.
Yeah. I did that. So
by the way, participants, you can also write your comments in the chat box, or just speak up, whatever you're comfortable. Yeah.
Okay. So normally what I do is I show a small experiment of what we did when we did with Echo along with Baba. So we made such small experiments, and then we went on to explain it. So without wasting time. So something is floating. What principle gets associated? Archimedes principle. And if we introduce to the class, we say today we will study Archimedes principle, and then we read this definition, and then we go on to explain. My goodness, what is the outcome which is going to be there? All of you can well imagine. Such a difficult language. The upward buoyant force that is exerted on a body immersed in fluid. My goodness, I can't even read it properly. So very difficult. So can we just say that something which displaces fluid, and the amount of fluid displaced is less than the amount, the weight of the body, it sinks. If it is the weight of the fluid displaced is more, it will float. This is how it is. And then we can get into the nuances of this particular principle. Now, how to explain this particular piece? So what I normally do is I write on my iPad notepad and then cut paste this over here instead of writing it while in normal classes I write as well. But some of the things I do it like this. Dr. Lata is saying something. Let me just see. What does she say? She says definitions made by. Oh yeah, I fully agree that definitions makes it so very difficult. So you should come to these definitions in the end rather than introducing them in the beginning. So as you can see, this is the diagrammatic view of the bottle which was shown earlier, and the bottle is completely full. When I say completely full, right up to the cap, and there is a reason for that. And the dropper is floating because dropper has an air pocket there. Okay. Now, if you were to draw a free body diagram, again, very complex word, so I'll not use it. If you were to say that there is a force going up, taking it up, which is buoyancy because of the air filled in the dropper, which is FB, which is the force due to buoyancy. And there is a downward force. What does the downward force comprise of? It comprises of the iron nut, which is attached to the dropper, the water inside the dropper, not complete dropper, but a part of it. And that is FW. We can say the force due to the weight. Right now, the buoyant force is more, so it is pulling it upwards and the dropper is floating. Okay, simple. Everybody understands? I mean, I'm not making you understand. I'm just simulating. You're all teachers. Then what I do, as Lata said, that I press the bottle. I certainly did. So when I press the bottle, it is almost impossible for a human being to compress fluid, the molecules, and then you can go get onto the physical construct of a fluid as to molecules are so tightly packed, and take that part as well, because everything is interconnected. A chemistry teacher asked me, can I attend? This is a session on physics. I said, I don't take these distinctions at all, that you are a chemistry teacher and you cannot attend. So again, coming back to the topic. So when I press it, I cannot press the fluid. So what does the pressure do? Pressure of my hand, which is pressing the bottle, it compresses the only air pocket which is available inside, which is inside the dropper. So what happens is more fluid enters the dropper and it compresses the air. The moment more water enters, at some point in time, the downward force, because now the weight of the water is more, plus weight of the nut becomes more, and it comes down. When I release the pressure, again, the air pocket expands, the fluid comes out, and the dropper goes up. Simple. Okay. Now, where is this used? I mean, why am I studying this? As a magic trick or something to excite the kids, it is good. Maybe to understand Archimedes' principle, it is good. But is it used somewhere in the real life? Any idea? So it is used in submarines. This is how a huge body of piece of steel floats and sinks. So it has got chambers where, as you can see now, which are empty. When they are empty, the submarine floats. When you take water inside, the submarine sinks. Simple. So what did we actually make? We made a submarine at home.
Wow.
Oh.
Isn't it? Such a simple thing. Okay.
And Sharad, just a query: how is the pressure in submarine? How is the pressure applied? What is
So Rahul, there are pumps which pump out the water.
Okay.
So they
got it.
And when they want to sink, they will just open the openings and the seawater.
Right.
And it sinks.
Got it.
Without it.
Cool.
And those of you who would have seen the recent movie of Avatar, what is it called? The one which is made in sea. They attach balloons to that huge aquatic fish, the animal which is there, and bring it to the surface.
Oh.
I don't know whether you recall.
No, I don't.
Okay. Okay. So now going to the next one. Now, this experiment, I'll not explain because there are a lot of concepts behind it, but I'll show the simplicity. I just wanted to introduce to the simplicity of the experiment because the experiment per se is very simple, but the concept behind this is very profound. And the things which are used in the experiment are also very simple. So this is what I wanted to convey to you. So let's see this.
Now we will do a very interesting experiment. As you can see here, I have got a 1.5 volt battery, and on the either end of the battery, positive side and the negative side, I have put two safety pins electrically connected. That means they are tightly pressed against these terminals, and I have put an insulation tape around it like this. Can you see it now? Okay. And in the center, I have put a small magnet like this. You know where I got this magnet from? Anybody identifies this? This is a magnetic door closure. Now, when you break it open, when it gets damaged like this, cracked or anything, then you get a magnet like this from inside. When you break this open, you will get a magnet. So don't throw this away. Take this magnet out. And then we have a coil, a very small coil with two ends straightened up and insulation removed. Now let's do the experiment.
So this is what I tell children. I will get on to the experiment, but just wanted to emphasize this point that don't throw your old toys away right like that. There are so many interesting things, geared wheels, electric motors, a fan belt, and so many things can be retrieved from it and can be used in so many experiments. So as you can see, something like a door closer is used here, and I got the magnet. I could have ordered them from Amazon, but why should I? I have 25 such magnets gathered over a period of time. Let's get on to the experiment. Any guesses what this can be? What experiment is this? Okay, let's see.
Now we will do a very... Start the experiment. I put this one end of the coil inside here and the other end inside here and straighten it up.
Yeah.
Straighten it up and give a gentle push to this coil.
Yeah. Motion through electricity. It's like a motor.
What do you see? What is happening? It's an electric motor.
Electric motor, exactly.
Okay, so we have made an electric motor and with such simple contraptions, such simple things which are available at home. I'll not get on to explaining as to how it works and all that. That would be a class in itself. But what I'm trying to say is just teaching about electric motors. I think it comes in class 9 or class 10 physics when we read about electromagnetic induction.
Induction. Yes.
Yeah, we read about
and those diagrams are so boring, Sharad. No, I still remember they make us draw these diagrams, right, of motor or generator, and no,
correct.
Yeah. So yeah.
Is it based on this aspect that you have the left hand rule or the right hand rule, something like this we had to study?
The Fleming's left hand rule. First is the Ampere's thumb rule. So it says that if there is a current carrying conductor and you hold the current carrying conductor in your hand like this, and the curl of the fingers show or the thumb shows the direction of current, then the curling of the finger shows the direction of magnetic field. So that is the first thing which comes in electromagnetic induction. I mean, sometime, Rahul, if our friends are interested, I can take a complete session on electromagnetic induction. We did this, Bama and I, for echo. In 3 sessions, we completed everything related with electromagnetic induction.
Wow. No, we'll definitely do it for children or for the school teachers. Yeah.
Correct. So that comes first, the Ampere's right hand thumb rule, and then the left hand rule and the right hand rule, depending on whether you are talking about a generator or you are talking about a motor.
Right.
So that's how it is.
Start the experiment.
Now, getting on to the next piece. Sorry, I'm not explaining this piece. I mean, we have time constraint.
Yeah, that's fine, Sharad. Yeah. It's better to show multiple things and talk about how teachers can improve their methods. Yeah.
Sure, thanks. Now, this is what Galileo said. I mean, and it is such a profound statement that mathematics is the language in which God has written the universe. When somebody way back in the 16th century said that, it's really amazing. And everywhere we find this, that all these physical phenomena can be described in terms of some mathematical equation. And indeed, that becomes the language. I mean, you would recall that Einstein was a patent office clerk. He must have gone to some laboratories, but what he wrote in 1905 and 1915, when special theory of relativity and general theory of relativity came in, was purely his thought process, and he wrote those mathematical equations, which are now the equations which are governing the universe. So indeed, mathematics is the language of universe. But for teachers and for
Galileo
students,
was the one who said that the sun is the center of the universe, and he was
Copernicus was first one. Copernicus was first one, Lata, and then Galileo went on to prove this and also gave the laws of planetary motions.
Okay, Galileo was imprisoned and he was blinded. I think I remember reading something.
I don't recall that. Okay, now this becomes a big problem for us, because the moment we go to higher classes and we start getting into the mathematical part of physics, then some students find it very interesting, because they feel that if they can crack numerical problems, they'll get good marks. Some people try to sort of mug up the steps, but the beauty of the math behind physics is lost. So I thought I'll show you some experiment and again bring out the beauty of the math behind the physical phenomena. Let's see something, a small video on this.
Thank you, Bama. The introduction was really very good.
I'm thanking Bama because this is a part of our echo. So Bama was introducing me. I'm thanking Bama because he really helped me in reviewing my videos and making them better.
And Bama is here among the participants.
Thank you, Bama.
Hi, Sharad. I'm enjoying your talk. Thank you.
Bama, at the end of Sharad's presentation, if you can add few words. Yeah, sure, Sharad. Yeah. No, please go on.
Okay. Yeah, please.
Thank you, Bama. The introduction was really very good. Now let me give you one example. Here is a formula for number of images formed when two mirrors are kept at an angle. N represents the number of images and theta angle between the two mirrors. If you tell students about this formula, just like this as is represented on the paper, they will not understand much about it. But now let me show you by actual demonstration. If you can see here, two mirrors are kept at an angle of 120 degrees and the number of images seen are 2, which conform to our formula where 360 by 120 is 3 minus 1, 2. Now let us keep the mirrors at 90 degrees. What do you see? We see 3 images and the flower itself. So 360 by 90 is 4 minus 1, that is 3 images. Now we keep the mirrors at 60 degrees. How many images do we see? We see 5 images, which also conforms to our formula. Now some questions still remain. First question can be, how an image is formed in a mirror? Second can be, why there are multiple images when 2 mirrors are kept at an angle? Third can be, why number of images increase when the angle between 2 mirrors is decreased? And one exciting question can be, if the number of if the angle between 2 mirrors is 0, as
I
per
was
the
going
formula,
to say
we
that.
should get infinite images.
Yeah.
Do we see infinite images? We will examine this in our workshop.
So what we have done here, I mean, instead of explaining this, what we have done here, we have explained a phenomena in the language of mathematics. Just a simple 360 by theta minus 1 is the story here. And we can do so many things. We can predict, we can examine boundary conditions. When I say boundary conditions, one of the boundary condition is when theta becomes 0. The formula says infinite images. Where do we see infinite images? Do we?
In the maze, when we are inside the maze.
Yeah,
when we have mirrors on both the sides, right?
Oh, of course, yeah.
Opposite sides.
Opposite sides.
Yeah.
When we are standing between 2 parallel mirrors, you see image inside image, inside image, inside image. And
that's what we get to see in the barber's shop.
That's right. The barber put a mirror back and show you how is the haircut. But again, that brings to our next question. I mean, infinite is infinite. Why don't we keep seeing images, say 100th image, 250th image? That's another question which can be discussed in the class. So interesting things can show up. As against, imagine a class where the formula is introduced, some diagram is drawn, and then the student is given some value of theta or number of images and asked to find out number of images or find out the angle between the mirrors, and the whole thing is up. So disinteresting it would be. So
Chetna says trial room. That's another good example.
Yeah, that's right. That's right.
Yeah.
Okay, so shall we move ahead?
Thank you.
Okay.
Yes.
I strongly believe that the mathematics teacher and science teacher in a school should have a very frequent conversation. And here I've just written a couple of lines, but the synergy which they can draw from each other is tremendous. Like mathematics teacher would, if the students are not asking, but this will be somewhere in their mind, why should I study this topic? Why should I always find out the value of x? Why should I study trigonometry? I mean, what does sine theta, cos theta has to do in my life? And mathematics teacher will be able to answer. He will say that, look here, Madam so-and-so is going to teach you this subject, and this is where this thing will be very helpful to you. You will be able to figure out this very quickly in a mathematical form. And what happens for the science teacher? Science teacher also will be able to say that, look here, this is how you did this in mathematics. Now let me apply, and how beautifully this concept will be explained. So it becomes so synergistic. And for example, I'll give you some example. We'll not get into the theory part of it, but whether it is easy to push a ground roller or is it easy to pull a ground roller? Now, apparently, without getting into the mathematics or physics of it, you will assume that the ground roller is of the same weight, whether we pull it or push it, the same friction on the ground with the roller. maybe with the same angle we are pushing the roller or pulling the roller. So why should it make a difference? But draw a diagram there. If you are pulling it, then there is some component, some f cos theta in the vertical direction, some f sin theta in the horizontal direction. Maybe I'm not getting into the complexity part, but mathematics comes in and it very clearly shows that it is easy to pull than to push. So there you go. It becomes so very easy. The mathematics teacher teaches about scalars and vectors. Why should I have those caps on the characters and I need to multiply those and it gives me something? Becomes so very esoteric for a mathematics class student. Why should I study vectors? But when you come to electromagnetic induction, maybe in class 10, maybe not in class 10, but in class 11, where you start studying about the dot product and cross product, and what Lata was mentioning about the left-hand rule and right-hand rule, where the two vectors are perpendicular to each other, and the third vector is perpendicular to both of them, which is nothing but a cross product, which you study in vector multiplication. So you can see how synergistic it is. And if these two teachers interact with each other, they can really make the students' life very, very happy. Do you agree with me?
Very true.
Yeah, totally. And Sharad, to extend your argument, in fact, different science teachers should also interact. One is math and science, the other is physics, chemistry, biology. Right?
Yeah, like my sister is a biology chemistry teacher, and she says that so much of chemistry happens in human body, and then biochemistry is so related, and biology is so related, and so on and so forth. You can go on and on. So I feel, and not only we should not stop there, Rahul.
Yeah.
In fact, we can get into the non-science subjects. We can get into social science also.
Yeah. True. In geography, they talk about a lot of things, which have some underlying science and right.
Yeah.
Exactly.
So
yeah, this particular example you shown, no, Sharad, scalar and vectors and pushing and pulling.
Yeah.
You just need a spring balance and a heavy rock, and so easily you can show this experiment. You can prove it experimentally. You can show whether pulling or pushing is better, and the same thing in the same thing mathematically you show the same thing, and the numbers actually tally quite easily. It's not a very difficult thing to show both.
Yeah. True,
and therefore, Sharad and Bhama, in history, we also, learn about how, let's say, ancient human beings, they developed certain tools, right? Which kind of change the civilization's course, and there are these simple principles behind it that you're talking about, right? Why they made certain tools and used them in certain ways. Yeah.
In the next slide, I'm coming to that. I made a very bold statement that we are wired for physics. I'll show you how our brain is wired, how we have evolved with the wiring of physics.
Right.
Yeah. Another thing is, the science teacher, they should give real life examples of whatever they are teaching. I've just picked up one small thing called resonance. We can talk about tuning of musical instruments. All these musicians will be doing tuck and tightening the strings and doing so many other things, because they want all the musical instruments to play in harmony. You extend it beyond that. We study in physics that the armies, when they are crossing bridges, they are asked to break their steps. Otherwise, the bridge may fall.
Yes.
I was taught, but I never understood at that point in time why it is.
Right.
But this can be very easily explained. People walk with about 2 steps per second. And that means within a second, the body will oscillate on one side to other side. And if this frequency of oscillation matches the natural frequency of the structure, then it will bolster its oscillation and oscillation. So give examples to them, like Tacoma Bridge collapse. Jivanshu, you have a question? Okay. So give them examples. Give them examples which they can go home and see in YouTube videos and come back and discuss in the class. They will be so excited that, ma'am, we saw this, sir, we saw this, and this is how it happened and why this happened. Maybe perhaps they have some questions. Now getting on to the second one. Brain is wired for physics. Why do I say that? We are pushing a car. All of us would have pushed a car or a school bus or something in our lives, right? We try pushing. The car doesn't move ahead. What do? We take 2 steps back and then push it again. We incline ourselves further.
Yes, yes.
Isn't it?
Right.
Nobody
right,
told
right.
us to do that. Nobody taught us. We have perhaps are not even science students, but all of us will take 2 steps back.
Intuitively we do that. Yeah.
Intuitively we do that, right?
Yes,
Why
yes.
do we do that? Because our brain is wired that the force in the horizontal direction will increase if we incline ourselves more toward with respect to the ground. Bouncing the ball, we are bouncing the ball against the floor, or we are bouncing the ball against a wall. Newton's third law of motion is wired into our brain even before Newton put it on paper. So we throw the ball to the wall slowly and we move forward to catch it. We throw it hard and we move backwards to catch the ball, don't we? Nobody told us to do that. We discovered ourselves. Catching the ball, those who have played cricket, they would know that
everybody.
If we keep our hands steady, then the ball is likely to spill out. But if we recoil our hand, then the ball will remain with us.
Everyone who has played cricket knows this. Yeah.
Exactly. And nobody.
Can I add one more thing, Sharad?
Yeah.
Please go ahead.
Yeah. So while even when small children are learning to walk, they apply the concept of center of gravity to balance their body. So we do this unknowingly as children also. So that suggests the same thing that you're trying to say, that we are wired. Even before we know all the information. So even
and thank you,
childhood.
Monica. So Sharad, so you and Monica should also connect sometime. Just to introduce quickly, Monica has been doing exactly the same thing, Sharad, what you do, and she lives in Ahmedabad.
Oh, wonderful.
She also takes a session called Science is Fun, and she's also done some amazing work. Yeah.
Wonderful. Yeah. And Monica, in some form or manner, this is what my last thing was: spreading and piling your hands while walking on a narrow brick wall.
Right.
Intuitively, we will spread our hands, because now I had taken a complete session on this in Echo as to why do we spread our hands? Why does a rope walker carry a long bamboo with him or her when walking on the rope? And we can go on and on and on. So I will. Sorry.
No, that is what those are still for adults, but even if we talk about children, like a 1-year-old child who is learning to walk, they are intuitively using these abilities. So yes, you are really correct about that. Your brain is really wired. That is what I wanted to emphasize. Thank you so much.
Thanks, Monica. Okay, we move ahead. Now I want to introduce to a wonderful tool called GeoGebra. Some of you are using it. Anyone?
Has someone used this one? No? I've heard about it, but I've never used it, Sharad.
So I strongly recommend, and I'll describe this to you. If you have not,
very useful.
Please do that. This is an amazing word. Hey, Rahul, if we extend it a little bit, is it okay? About 10 minutes?
Yeah, definitely. And we'll keep some time at the end for Q&A also, Sharad. So maybe we'll, sure.
So let me introduce. This is an open source tool made by Google, and this has got a rich repository of tools to teach mathematics and physics and whatnot. Now, you don't have to learn this tool to use it. All over the world, people have made various small projects in this. And the beauty of this is it is all, on a sharing. You can't make a project and keep it for yourself. This is based on the principle of education is free and should be shared, democratization of education. So you make something over there and it is available in the library. And there are millions of such things in the library. Now, if you learn the tool, good, you can make something for yourself. But if you don't, just go there, pick up what you want and use it. So this is what I'll show you now.
What others have done, right?
What others
That's
have
so
done.
amazing.
Yeah, it's truly amazing what people are doing. Just 1 second. Let me go to GeoGebra. Give me a minute.
Sure.
So this is GeoGebra. Just 1 second. I'll go to the home page. Yeah. This is what home page will look. I'll remove this one. Yeah. GeoGebra for teaching and learning math, though it's written math, because it has got so many powerful calculators and graphing calculators and scientific things, but it has got wonderful animation capability. Okay, so you can go and keep on exploring. When you go to resources, GeoGebra, community, curriculum, elementary maths, middle, high school, and then you can see the subjects over there and so on. You can explore, you can go on exploring. I'll not spend time telling you about this, but I also didn't make anything. I didn't learn GeoGebra. I actually selected a few and put it in my favorites. And here are my favorites, because I was teaching laws of motion. So I pressure, something on kinematics, sound. So I've made them favorites. And
can you show one of these, Sharad, just for
I'm coming.
Rahul,
I'm coming to that.
Sure.
And you will find it amazing, huh? So what I did was, when I was teaching, I think class 9 physics, when I was teaching the graphing, which is time distance graph in physics. So I use this one, the third one, and I'll open this. Okay, there are various sections. I'll go to a particular section in this so that we get on to what we are looking for. I go to velocity graph number 1 and I make it full screen. Okay, all of you see this?
Yes.
Now this is a beautiful animation tool available to you, ready to use. You don't have to pay anything. You don't have to learn anything. So there is only one checkbox ticked out, which is road. And on the road, on the left-hand side of the graph is empty at the moment. What you see is a red car on distance 0. And time is 0 at the moment. Now what I am doing is I'm telling the class that I have got a what do you call this drone camera on the road, and every second it will take a picture of the road. Every second when it takes a picture of the road, it will paste it over there in the particular second column. So at column 1, it will paste the picture taken on the first second, and so on and so forth up to 10 seconds. Okay. Now see what happens. See the fun of it. So I'll say put the pictures. So at 0 second, it has put the picture on the 0th column, right? Now I start moving. I'm manually moving it. I'm not playing it. So I move it. So on the first second, it took the picture and saw that the car has moved ahead at 20 meters. And it has taken the picture. My hovering camera has taken the picture and I have pasted over there. Third second, third second, the car is moving. Okay. Now I move on to 4th second, still moving. Then what do I see? Then in the 5th second, it stopped. it remained where it was at 100 meters, right? So as you can see, on the 4th second, it had reached 100 meters. 5th second, also it was at 100 meters. So the picture shows that the car is there itself. Then I go further, increase the time. 6th second, still not moved. The car is standing. I move further. 7th second, oh, it started moving after stopping for a while. The car has started moving, and it, up to 10 seconds, it kept on moving. So this is what it is. Simple. Now what I do is I go and put markers over there. Some markers have come, red dots. I remove the photos and I connect the graph. What do I get? A time distance graph.
Yeah.
Everybody will understand.
Yeah.
Okay. Let me get to a complex one and then I'll tell you a story.
Right.
So I get on to the 5th one right away. Yeah. So I'll not explain it anymore. I'll just keep on moving. So I say photo and I'm moving.
How do you move it, Sharad, manually? How do you?
There is something down below, Bama, as you can see, there is a dot and a line. That is a slider and I'm moving it.
Oh, I see. Yeah, yeah. Okay.
I could have played it like this right away.
Okay, okay. Understood. Yeah.
Does this have two cars, Sharad? One blue and one green.
And the bike.
There is
a bike.
So there is a
truck and a car and a bike.
As you can see, blue colored truck, which is stationary on at meter 140.
Right.
There is a car which is moving upwards on the other side, away from us, and there is a bike. Now, what do we notice here? You can ask the children, what do we notice here? We notice that the bike seems to be moving faster.
Bike is about to overtake.
It is catching up with the car.
Yes.
And it is caught up with the car. And
Yeah.
it moves further. It overtakes the car and so on and so forth. There we go. Right? I do the same thing. I remove the picture. I put the marker.
Draw the graph.
Draw the graph.
So truck has remained stationary and the bike has moved at constant speed and car also, but bike is faster.
So many concepts. Yes.
Yeah, exactly.
Horizontal line shows that I'm stationary. Inclination of the line, the more inclined the line, it shows that it is faster. Green is less inclined, so it shows slower. Wherever the two lines are intersecting is the point where the other one overtakes the other one, and so on.
Yeah, beautiful.
At the 10th second, which vehicle reaches where? One reaches at 140 meters, the other one reaches at 200 meters. So many things. You can go further on. You can say tan theta, and you can take the inclination and
slope and
I'm not getting into all that.
But and what you said, Sharad, earlier was right. That after this kind of a thing, only formula should be introduced. Then they become so easy to understand.
I'm getting onto something more now. Much more interesting than this. So what I do now, based on this, I tell my class, or I actually told my class, and I'll sorry. So this is my notebook, which has it changed for you? No.
No, we see the same graph, 3 graphs.
No.
Why? This showing recording is stopped or something like this. I think now it will come. Shall I unshare and share again?
Maybe you can do that then.
Share content, share screen. I think sharing at start.
Okay. Now it's coming, Sharad.
Yeah.
So you are, Yes. Now we are back to GeoGebra. Yeah.
No, this is not GeoGebra. This
Okay.
is my notepad.
Your notes. Okay.
Okay. So this is my notepad where I
Tortoise and rabbit.
so I teach I take my classes on this one. So what I've done is I have drawn a graph similar to what was available on GeoGebra. I have drawn the track over there, and I ask the students, I say, hey, listen, all of us have read the story of rabbit and tortoise. Rabbit ran very fast, then rabbit went off to sleep, and tortoise kept on going steady and won the race. So can we graph it? Can this story, instead of being in English, can be narrated in form of a physics graph? So children get excited. So I ask them, the rabbit is yellow, tortoise is orange. Let's do the graph. So I ask them, if rabbit is moving faster, how the line should be drawn. And now they have already seen it. So they tell me that will be more inclined, or they'll be sort of less, depending on which axis you are talking about. So let's put it, say, here. So I put it here, and I take the orange color and I put it here. So after 30 minutes, the tortoise could reach only 20 meters, whereas the rabbit reached 60 meters, right? The rabbit looked at the back and he couldn't see the tortoise. And rabbit said, hey, come on, I'm quite ahead. That guy is still not seen. Let me take some nap. And then in any case, I can finish and I can win the race. So he went off to a long, oh, I'm sorry, not this color, yellow. He went on to a long sleep. Okay, he kept on. Then I asked, for how long do you want the rabbit to sleep? Somebody will say 1 hour, somebody will say 2 hours. I mean, it's fun. The rabbit kept on moving at the same speed. And
the tortoise, yeah.
Tortoise. And reached. This guy wakes up. This guy wakes up after some time. The rabbit wakes up after some time and runs very fast, but finishes after the tortoise. So, Aesop's fable in physics.
Yeah.
Now nobody will forget. After this, for sure, nobody will forget how to make time distance graphs in physics.
Yeah. True.
Okay, so coming back.
Interesting. This is quite useful tool, GeoGebra, right? This was, of course, not on GeoGebra, but
this
the
was,
one that
of
you showed
course, not
before
on
this.
GeoGebra.
But what you showed.
So going to presentation again. Where are we now? This. So we are at the end. Now, one more thing, Rahul, I just wanted to show you.
Sure.
Another technique which I use, and some of you may find it interesting. I use this notepad. Let it come up. I use this notepad, and you can use any notepad. And what I do is, I will show you. Yeah. So what I do is I make my lesson plan like this. So I say this must be class 8. Force and pressure. I write some questions. I copy from the textbook, PDF, and I leave some spaces like this. I copy the diagrams like this. So this is my skeleton, which is ready now. Okay.
Right.
With a lot of spaces in between, a few things written here and there, and a few things and a lot of blanks. Then look here what happens in the class. I'll go to the punk class. What happened in the punk class? So first I added the one more page. I took attendance over there. I got onto the class. And then I started discussing, and whatever student said, I started writing over there. Then we got onto this particular sheet. Then we started working together in the class itself.
And students are seeing this, Sharad, right? While you are writing.
Students are seeing all this.
Right.
Then push, pull thing. Then I catch hold of two girls and I say, Anjali is here, Payal is here. Who is pushing whom? Whether Anjali pushing Payal, something which is shown over here, or Payal pushing Anjali, or both are pushing each other. Then I take a poll and say, tell me who is with 1, who is with 2, who is with 3, and so on and so forth.
Yeah, this makes it very interesting.
So this becomes very interesting. Now,
Fun and
this is with 1.
Mm.
I do it with another one, the same thing. No, not this one. This one. So here I was teaching some other students. Now you see, there was some more discussion over there. Again, I took my skeleton sheets, copied it, and I started writing over there. Same thing.
So whatever children are talking about, you are kind of writing there.
I'm kind of writing over there.
Which notepad is this, Sharad? What is this actually?
This is I'm using Notability. This is a very nice notepad called Notability, which I'm using on. Yeah, I'm using my iPad.
Sharad, I'll take the details later. So if there is some low cost option now, which let's say teachers could have, I'll talk to you about it. Yeah.
Sure. So as you can see, I'm filling up all the spaces which I had left, and these discussions are going on. Catapult example I gave, as you can see. So this is how Rahul I take my classes all on this.
Yeah, it becomes so interactive, and exactly.
It's almost akin to being in front of the class. And teaching them.
And what you are writing is just a summary of the discussion that is happening in the class.
Correct. Another thing which I do is I always log on from 2 devices, like I have done just now.
Yes, that
so
helps.
One, I'm able to see what I am writing, and I'm able to see the students also on the other device.
Yes. That is useful.
That is very useful.
Yeah, usually I do something similar with the PPT, with the skeleton put on the PPT. But I don't log into 2 devices, but this seems very nice. Yeah.
Very nice.
Another thing, Bama, what happens with PPT, the PPT, the pen features and the capabilities are very rudimentary.
Limited, very limited, yeah.
But if you go to a proper notepad, then
no, I use this attachable Wacom pad, writable pad, whatever that is.
Right. That's
so Rahul, sorry I exceeded my time.
No problem. I think it was quite interesting, Sharad, whatever you've shown, including the GeoGebra and your method of how you teach and so on. So friends, we can take another 5 minutes.
I just have a request. There's a Google form in the chat. Everyone can just please fill it.
Please fill the form that Shalini has circulated. I think that is for simple feedback.
Yeah.
And Sharad, thank you so much. So any questions, friends? Anybody who wants to ask anything to Sharad?
Bharati's hand is...
Yeah, please just start. You can, Bharati, you want to ask?
Yes, Rahul, yeah. I wanted to know, Sharad. Hello, Sharad. That was a lovely session.
Hi, Bharati.
Yeah. I wanted to should I look at those description and decide which Geo one to which Geo app to download, like, or which would be the? I take maths mainly, so.
So for you, there is so much of content. If you teach math, so you go there instead of just looking at everything which is there, which will take enormous amount of time. Suppose like I got interested. I was teaching somebody the formula for 4/3 pi r cube, the volume of a sphere. Sphere. Now I thought that there must be some good method of deriving that or explaining to them. So I typed volume of sphere, and it gave me tons of GeoGebra, whatever widgets you may call them.
Okay.
And I started looking at each one of them, and whichever I found interesting, I just said favorite, and it comes into my favorite. That's it. You don't have to do anything else.
And it must be easy to self-learn, right, Sharad? There's no tutorial required, right, for GeoGebra?
Zero tutorial. For using it, zero. For actually using it and making something of your own, you need to know how to use tools. But
a little bit of practice one
So
has
I
to
don't
do
have to
probably.
download the app you are saying.
No. You have to be connected online.
That's all.
It's
is it?
online.
That's all.
Yeah.
Okay. And as you said, search for whatever you are looking for,
Yeah.
and it would give you options, kind of.
It will give you options.
Okay. No, I was looking at like QMath uses GeoGebra, I know, to simulate certain things to explain to children. So
Okay.
I was thinking like because I use a simple kind of a editor tool, like I use the pen and do things and explain. So is there some tool wherein I can draw a triangle? If I give the coordinates, it just draws the triangle, something like that. So is it there in GeoGebra?
Bharti, these mathematical tools are so powerful. You give coordinates, it will draw. You give x1, y1, x2, y2 for a circle, it will draw.
Okay.
So there is so much available.
But I don't have to download any of these apps.
No. You don't have to do anything. For mathematics, you will feel that you have got a nuclear bomb with you. I mean, in the right sense.
Okay. Fine. Thanks, Sharad.
Yeah. Welcome.
Okay, so any more questions? Bhama, Monica, you want to share something maybe quickly, since you both have been also very involved in creative science, pedagogies.
No, Rahul, actually, I understand, like, it was really a wonderful session from Sharad. It explains a lot. I also do things in similar line.
Yeah.
So yeah, it was really interesting. Yeah, but the equations part I really enjoyed, because I've never done such a thing before. So
Right.
maybe
Yeah.
I can connect with Sharad for later on.
Exactly.
Yeah.
Surely.
And I think all of you are anyway in that WhatsApp group, and if you want, we'll pass on the contacts.
Yes.
Yeah.
No. Sure. Thank you so much.
Yeah, even I would like to connect with Monica.
Monica,
because,
yes.
So much I hear about your classes, sessions, and Monica. Yeah, how interesting they are for the children and all that. It will be really nice.
Sure. You can attend any of my class. Well, by the way,
I'll do that.
right now the children are on their own for now. So, but still you can definitely.
We'll share the link, Bhama. And Monica, just to introduce Bhama also has been working quite a bit in Bangalore with school teachers. She has been doing this kind of work for years.
That's great.
She also has
in
developed.
fact, Rahul, we should ask Bhama to present, because she.
That's what I was thinking. Yeah.
It was such a big learning when we worked together for.
Right. Exactly.
Yeah. No. Yeah. Thing is, I don't know exactly what to. Yeah. We'll. What to present, because
Main thing is if you could convey to the teachers how they could adapt from these methods and make their own teaching more effective. So that will be a great thing.
Yeah.
And the real thing, I think, from Sharad, your thing is that learn by doing, right? That's the principle. Whatever subject one is learning or teaching, if one tries on their own, that's the best way to learn.
Actually, next week.
Sorry.
No, next weekend, I mean, the children, my science club kids are having a science fair. So each one is doing a small experiment and presenting. So all those in Bangalore can, are welcome to attend. In ICICI, in the faculty club, I will send out a mail, and
you could put a message on the WhatsApp group also.
Yeah, I'll do that. At least those who are in Bangalore can definitely attend.
Can come. Yes. Exactly.
This Saturday afternoon. So most welcome. Yeah.
That would be nice. Yeah.
Actually, what was saying is teaching physics is like explaining the environment around you, nothing else.
Yeah.
What we are teaching in physics is what is happening around you everywhere.
Exactly.
Till you get into really esoteric stuff and start dealing only with math and not physical explanation of things.
Right.
Exactly. It has to be really exciting. So one thing which I wrote over there, that for everything, give an example which children can relate to.
I think that's very important, Sharad, as well.
Yeah.
Actually, there's a question in the chat. Kavita is asking, so do you mean to say that teachers should know some maths before they start teaching science?
I mean, I would believe that somebody who's teaching science would have studied mathematics in any case up to school level. And that mathematics is good enough for...
It's good enough. Yeah.
The only thing is, think over and over again as to how do I connect the two. Connection is very important because everywhere there is connection.
Yeah. And this level of math is simple, not too difficult. Yeah.
Not too difficult at all. Like I really wanted to give that example. Bama, you will remember in our echo session, one teacher asked that there was a multiple choice question that if you go to the center of Earth, then as per the formula, the force of attraction F is equal to m1 into m2 divided by r square and into the gravitational constant.
That becomes 0, huh?
That should if r becomes 0, the force should become infinite.
Okay. Force will become infinite. Okay.
But it is not so. It is 0. So how do we explain this? So one way could have been that we just give some explanation and we are done with it. But Bama, if you remember, we actually...
It was a beautiful mathematical, very rigorous proof that you gave to show that it is 0. So mathematically you can show.
Mathematically we can show, and it'll get permanently embedded in the mind. So this is how we should actually... The idea is that should get embedded in the mind. We may do a few things, but then that becomes the habit of child to go ask a number of questions, why, and reach to the root of that particular question, rather than just taking something for an answer and mugging it up.
Right. True. Okay. So thank you so much, Sharad. I think that's very interesting, and we'll I think GeoGebra, we can all search on the internet the address, etc. And I hope some of us will start exploring that. And we have, I hope you all have learned something valuable today. Basic thing that, think of some simple experiments, relate with examples that children can connect to. So that is the thing that, that makes the class exciting.
Yeah, and don't throw anything considering it as trash.
Yeah. You can recycle stuff. Yeah, it's also good for the environment. Yes.
Thank you.
Exactly. Thank you so much, Sharad. Thank you.
Thank you.
Bye.
Please fill the Google form.
Already filled, Sharad.
Thank you.
Thank you. Bye-bye.